Title: MoFO. Momentum Filtered Optimizer for Mitigating Forgetting in LLM Fine-Tuning. Abstract: This paper proposes a new fine-tuning algorithm, Momentum Filtered Optimizer, MoFO, to address the issue of forgetting pre-training knowledge in large language models, LLMs. Unlike existing methods, MoFO does not require access to pre-training data and does not alter the original loss function. It iteratively selects and updates the model parameters with the largest momentum magnitudes, achieving similar fine-tuning performance while keeping parameters closer to the pre-trained model. Introduction. Large language models, LLMs, have demonstrated remarkable capabilities in various tasks. However, during fine-tuning, LLMs may forget the knowledge acquired in pre-training, leading to a decline in general capabilities. This paper aims to mitigate this issue by proposing MoFO. Motivation. The fine-tuning loss of LLMs has many minima, and these minima can vary significantly in their distances to the pre-trained model. The authors observe that minima closer to the pre-trained model are less likely to experience forgetting. Inspired by this observation, MoFO manages to approach closer minima by dynamically updating a portion of parameters that are most effective for reducing fine-tuning loss at each iteration. MoFO algorithm. MoFO is a replay-free and regularization-free method that iteratively selects and updates only the parameters with the top alpha% largest momentum magnitudes within each block. The blocks refer to the parameters of different parts of the network, e.g., weight matrices and bias terms. Contributions. The authors propose the MoFO algorithm, a new optimization method designed to mitigate the forgetting of pre-training knowledge during the fine-tuning process. They present an initial convergence analysis of the MoFO algorithm and conduct experiments on various tasks, demonstrating that MoFO outperforms existing methods both in fine-tuning performance and mitigating forgetting. Overall, MoFO is a novel approach that addresses the issue of forgetting in LLM fine-tuning without requiring access to pre-training data or altering the original loss function. It has the potential to enhance the performance and generalizability of LLMs in various tasks. The paper discusses the issue of catastrophic forgetting in fine-tuning pre-trained models, particularly Pythia 160 meters, using the Atom optimizer. It presents a novel approach to mitigate this problem by modifying the Atom optimizer to update only the subset of parameters with the largest momentum magnitude. This new method, called Momentum Filtered Optimizer, MoFO, is designed to keep the model closer to the pre-trained model during fine-tuning, thereby reducing forgetting. The authors first analyzed the loss landscapes of Pythia 160 meters after fine-tuning on a subset of the Flan dataset using both Atom and Lion optimizers. They find that the two training methods converge to different minima with similar fine-tuning loss, but Lion converges to a minimum that is significantly farther from the pre-trained model and archives a much larger pre-training loss. The authors then discuss how to keep the model closer to the pre-trained model by using the classical block coordinate descent (BCD) method. They propose updating only the parameters with the greatest influence on reducing fine-tuning loss, measured by the magnitude of its gradient. However, in the Atom optimizer, momentum directly affects parameter updates, while gradients influence parameter updates indirectly by affecting the momentum. Motivated by these discussions, the authors design MoFO, which modifies the Atom optimizer by updating the subset of parameters with the largest momentum magnitude. MoFO partitions all parameters into fixed parts according to the network architecture and selects alpha% of the parameter entries for BCD update within each part. The authors formally introduce MoFO in Algorithm 1 and illustrate its mechanism in Figure 2. They note that MoFO efficiently selects and updates the most influential parameters, as dictated by the momentum's magnitude, thus enhancing the fine-tuning process while alleviating the catastrophic forgetting of pre-training knowledge. The paper introduces MoFO, a novel optimization algorithm designed to mitigate catastrophic forgetting during the fine-tuning of large language models, LLMs. This approach utilizes a momentum-based optimization method with a filtering strategy to select the top alpha% of gradients for updating model parameters, thereby reducing noise and promoting a more stable optimization process. The authors demonstrate MoFO's effectiveness by comparing it with the Atom optimizer on various common-sense tasks and pre-training loss landscapes. Experimental results are presented for instruction fine-tuning and continual fine-tuning using Llama 27B and Tiny Llama 1.1b as base models. These experiments utilize datasets such as MetaMath-QA and Code Alpaca, which cover question-answer pairs from different domains like mathematical reasoning and code generation. The results show that MoFo significantly mitigates catastrophic forgetting and improves the performance of LLMs on these tasks. The paper also discusses the MoFo approach for fine-tuning LLMs to preserve their general capabilities while learning new tasks. It introduces a set of widely used benchmarks to assess the performance and catastrophic forgetting effects on LLMs after instruction fine-tuning, including MMLU, Common Sense, GSM-8K, and Human Eval. The MoFo algorithm is compared with several baseline methods, such as full fort, L2 regularization, L1 regularization, and half fine-tuning, HFT. The results demonstrate that MoFo achieves comparable performance in the math task while significantly mitigating catastrophic forgetting of general capabilities. Overall, the MoFo approach demonstrates its effectiveness in preserving general capabilities while learning new tasks, making it a promising method for fine-tuning LLMs. The paper addresses the issue of catastrophic forgetting in large language models, LLMs, during fine-tuning on new tasks, proposing a novel algorithm called MoFo. This method aims to mitigate this problem by optimizing only a fraction of the model's parameters during each update. The authors evaluate MoFo on various benchmarks and compare it with other methods such as full fort, HFT, L1 regularization, and L2 regularization. In the coding generation task, MoFo achieves comparable performance to L1 regularization and outperforms full fort, HFT, and L2 regularization by more than 3% on human eval accuracy. It also shows the least degradation in general capabilities compared to other baselines, with an average accuracy reduction of only 1.1%. In the continual fine-tuning experiment on the trace benchmark, MoFo outperforms full FT and HFT by at least 1.4% on the OP score and by at least 4.7% on the BWT score. Combining MoFo with traditional continual learning methods like replay and GEM further enhances performance. The paper also conducts a further analysis of MoFo, investigating the impact of the update fraction of parameters and exploring different update strategies within MoFo. The results show that with a moderate parameter update fraction, MoFo can preserve pre-training knowledge and significantly enhance fine-tuning performance. Additionally, the authors compare MoFo with two other BCD methods, randomized BCD and gradient-filtered BCD, in terms of performance on the math reasoning task, GSM-8K, and accuracy changes of general capabilities. MoFo significantly surpasses both gradient-filtered BCD and randomized BCD, indicating that updating parameters with the largest momentum leads to strong optimization power. Finally, the paper reviews related works on catastrophic forgetting, particularly in the context of LLMs, and highlights the growing body of recent works focusing on the forgetting of models' knowledge during the fine-tuning process. In the realm of machine learning, researchers have proposed numerous methods to alleviate forgetting in continual learning. These methods can be categorized into three primary approaches: replay-based methods, regularization-based methods, and architecture-based methods. Replay-based methods leverage past experiences to facilitate the learning of new tasks, while regularization-based methods introduce constraints to preserve old knowledge. Architecture-based methods balance the goals of learning new knowledge and keeping the old one through model architectural modifications. Block coordinate descent, BCD, is a method that has drawn attention due to its ability to prioritize coordinates that yield the most substantial improvement in each iteration, thereby potentially accelerating convergence. In the context of machine learning, BCD has found applications in memory-efficient fine-tuning of large language models and federated learning. The paper discusses the issue of catastrophic forgetting in large language models during fine-tuning, which is a common problem in machine learning. The authors propose several techniques to mitigate this issue, including using a combination of pre-training and fine-tuning, applying different learning rates for different layers, and utilizing knowledge distillation. They also explore the use of gradient episodic memory for continual learning and the importance of maintaining plasticity via regenerative regularization. Furthermore, the paper highlights the significance of understanding the trade-off between generality and speciality in fine-tuning foundation models. It emphasizes that while general capabilities are essential for domain-specific models, they should not come at the expense of forgetting previously learned knowledge. The authors provide an extensive review of existing literature on catastrophic forgetting, including various methods proposed to address this issue, and underscore the need for further research in this area to develop more effective techniques for mitigating catastrophic forgetting in large language models. The research paper provides a comprehensive overview of various techniques and methodologies in machine learning, particularly focusing on coordinate descent methods, lifelong learning, and large language models. The authors discuss the efficiency of coordinate descent methods on huge-scale optimization problems, as well as the importance of choosing the right rule for faster convergence. They also delve into the concept of lifelong learning, which aims to enable machines to learn continuously from new data without forgetting previous knowledge. The paper highlights several key findings and novel ideas in the field of machine learning. For instance, it discusses the role of task-specific skill localization in fine-tuned language models and the impact of scale on catastrophic forgetting in neural networks. It also explores different approaches to overcoming catastrophic forgetting, such as experience replay and orthogonal subspace learning. Furthermore, the authors discuss the importance of benchmarks for continual learning in large language models, such as the trace benchmark, and various paradigms for efficient meta-lifelong learning with limited memory. They also touch upon the concept of dynamic growth for instruction tuning data curation and the use of synaptic intelligence for continual learning. In terms of algorithms and mathematical concepts, the paper explains the iteration complexity of randomized block coordinate descent methods for minimizing a composite function and the convergence of a block coordinate descent method for non-differentiable minimization. It also details the use of gradient core set-based replay buffer selection for continual learning and the application of sketching for communication-efficient federated learning. The authors reference two papers: Atom Can Converge Without Any Modification on Update Rules, by Zhang et al., and Model Tailor. Mitigating Catastrophic Forgetting in Multimodal Large Language Models, by Zhu et al. They provide a proof of Theorem 1, which involves defining a norm parallel top alpha % in ROAD. This norm is defined as parallel z parallel top alpha % equals z circled dot operator s parallel 2, where S is a vector that filters out the top alpha % of the entries in Z. The authors show that this norm satisfies the properties of a norm, including positivity, homogeneity, and the triangle inequality. The proof of Theorem 1 relies on the definition of the norm parallel top alpha % and the properties of the filter S. The authors show that the update rule of the MoFO algorithm can be written as theta t plus 1 minus theta t equals minus eta tmt circled dot operator filter t, where filter t is equivalent to the filter S. They also define a greedy filter, which is used to filter out the top alpha % of the entries in a vector. They show that this filter satisfies certain properties, including the fact that it is a norm. The proof of Theorem 1 is based on the definition of the norm parallel top alpha % and the properties of the filter S. The authors show that the update rule of the MoFO algorithm can be written in terms of this norm, and that it satisfies certain properties. They also provide a lemma, which shows that the norm parallel top alpha % is indeed a norm. This lemma is used in the proof of Theorem 1. The paper introduces MoFO, a novel optimization algorithm designed to improve the efficiency and effectiveness of gradient descent in machine learning model training. MoFO dynamically adjusts the learning rate based on the norm of the gradient, with a parameter alpha controlling the proportionality constant. This allows for adaptive learning rates that avoid large updates when gradients are large. The authors provide a mathematical derivation of MoFO and analyze its convergence properties, showing it converges to a local minimum under certain conditions. They compare MoFO with other optimization algorithms such as stochastic gradient descent, SGD, and Atom, demonstrating its effectiveness in various experiments. Experimental results using MoFO for fine-tuning pre-trained language models on different datasets are presented, showing MoFO outperforms other optimization algorithms in terms of performance and efficiency, especially when fine-tuning large models. Implementation details for these experiments are also provided, including specific hyperparameters used for each dataset and computational resources required. Overall, the paper presents a novel optimization algorithm that can be useful for improving the efficiency and effectiveness of machine learning model training.